I'll just say the illustrations are simple. Projecting them is more difficult.
Good.
All right.
Which button goes forward? Which button goes backwards?
The down one goes forward. The top one goes up. And you've got a little bit pointer.
Okay, the bottom one goes
down. Yep.
And I have half now, right?
Yeah.
Okay.
Okay. I know we're all anxious to go see what's out at the coffee break, but Jasper Nice from, I think you said you were from Edmonton.
That is correct.
Almost local. Simple 3D illustrations in the tech ecosystem. And as I've seen in the past, while it may be simple in the tech, connecting the computer to the projector does lend a few problems. So Jasper.
Thank you very much. Hello, everybody. Oh, I'm not going to use the microphone. Can everyone in the back hear me? Yeah. Awesome. Before I get started, I just want to say a few remarks. I want to say thank you for everyone who came. I want to say thank you for everyone who wasn't able to come, but who is still part of our community. Thank you, Boris, and everyone else for hosting the YouTube chat. And if I know you through Tech Stack Exchange, hi. Should probably hold the remote. Yes, and I wouldn't be here presenting, at least, if it weren't for Barbara Beaton's suggestion. So thank you, Barbara, for suggesting this talk. We're going to talk about simple illustrations in the tech ecosystems, specifically 3D ones. We're going to start with, there are 3 sections. The first section has 3 subsections, the second section has 2 subsections. You can count. We're going to start with the overview. We're going to talk about the problem that I'm talking about. We're going to talk about why it's important. And we're also going to explore a bit about why I chose Lua LaTeX as my platform. Without being addressed. We are going to study something here called, this is going to sound scary, affine algebra. Ooh. We're going to motivate it though. We're not going to introduce it out of nowhere. This diagram is made out of triangles. Triangles are very special. Triangles are a type of simplex. A simplex is a line segment. In the context of this talk, a simplex is a line segment or a triangle. The interesting and very fascinating thing about line segments and triangles is that they are equivalent to bases in linear algebra, whereas I like to call them affine bases when they are not when they have a point of origination that is not necessarily the origin. In linear algebra, the origin doesn't matter. In affine algebra, the origin of a vector definitely matters. And so the cool thing about that is that when we represent a triangle as a basis, we can do a bunch of affine algebraic reasoning with it that lets us do 3D stuff. We will explore this as we go. So I talked to you about something called the simplex basis correspondence. That is what I like to call it. Every triangle is a basis. Every line segment is a basis. When I take the illustration of intersecting planes, I represent the triangles as bases, and I use Gauss-Jordan on their bases to find the intersection subspace. We will get into that later. Triangles are bases, and bases span something called subspace. A subspace, if a basis has 2 vectors sticking out of a common point of origin, subspace through that basis is the plane that's spanned by those 2 vectors. If you have 1 vector out of that point, the span of that basis is a line through that point in the direction of the vector. I hope that is clear for you guys. I'm very used to this stuff. We will develop it intuitively, is my plan, without too much fancy jargon. My hope is to not overload you guys with jargon. I want to introduce everything in terms of stuff that you can visualize in your head So that is the plan. This is a Klein model. You don't need to know the definition of a Klein model, but I'm sure most of us know what a Klein model looks like. Why is this issue important? Spatial illustrations are everywhere. The basic transformations, when we deal with affine algebra, there are two important parts of it. There are affine operations, such as addition, subtraction, dot product, cross product. These are fancy terms. Addition and subtraction are valuable for navigation of bases, of subspaces through bases, because when we do that, we take a linear combination or an affine combination of the protruding vectors out of the point of origination in order to navigate the plane through, say, a triangle. There are also transformations in affine algebra which are different from the operations. A transformation is accomplished through matrix multiplication. In linear algebra, we have matrix multiplications. Some of you who have taken linear algebra or taught it will know what these are. Some of you also know what affine transformations are. Affine transformations are linear transformations that include translation. So there are linear transformations that include translation, because that is not included in linear algebra. And that lets us do a lot of cool stuff in 3D, as you can imagine, because linear algebra gives you rotations, and affine algebra gives you translations. What am I doing right now? I'm rotating, translating. So, as I've mentioned, I'm going to drill this point home many times throughout this talk. A simplex is a basis. When all of these triangles here, when I tessellated this domain, this parametric function, I took a rectangular domain and mapped it onto 3D. This function jumps up through the ceiling. How did I stop that? I put an invisible bounding box, bounding cube of triangles around it, and I partitioned them by these triangles. The way I did that is I used something called Gauss-Jordan on their bases. Because when you take Gauss-Jordan, it's so cool. It lets you identify the intersections of two subspaces in linear algebra, but it also works in affine algebra and projective algebra. And what that let me do is I was able to identify the line segments which span the one-dimensional subspaces through both the triangles of the green diagram and the triangles of the invisible bounding cube. And then by extending those one-dimensional bases, I was able to identify the intersections with their parent triangles and partition those parent triangles by those intersection points. Afterwards, I was able to remove everything above this diagram that would have gone straight up into the ceiling using a Boolean filter. And we get this cool little image. You can see how it turns into a perfect grid when we look at it upright. The opacity of the plane is not that high, so you do not see it, the occlusion too well, but if you look closely here, it is actually more gray there, but probably not on this screen. I forget who suggested this diagram to me. I believe it was Barbara, but I might not be. I looked for the original citation and I could not find it. Parametric domains are often simplicity tessellated. Oftentimes there are other ways to do it. There are other ways to illustrate parametric objects. I really like simplices because, well, as I've described, the intersection of two simplices is a simplex, and it always reduces down to operations and simplices. It is very nice. So, this picture is wrong. Why is it wrong? We did not identify the correct intersection points of the line segments composing the gravity field and the intersections of them with the sphere. If we took the actual intersections, they would not be on the straight up triangles that comprise the sphere. They would actually be 1 unit away from the sphere's center, which is not always true when you intersect a triangle which is on a tessellated sphere, especially when you do it according to the Cartesian product of domain sequence sampling, which is the way everyone does it these days, unless they do Dillon triangulation. Why did I choose Lua LaTeX as a platform? This is actually a really cool story. It goes back to a conversation I had with Max Chernoff in the chat. Some of you were there for that. So I used to think math animations were the coolest thing, hands down. So I learned TeX. Some of you who know me from TeX Exchange will know that I've spent years posting about TeX on 2 accounts. I love illustrating. It is something that I just find so much joy in. This is not the animation in question. We will see that one later. This is a stereographic projection of a spinning sphere. I think it looks cool. I love stereographic projections. It's very similar to the diagram that took 16 hours to render 24 frames of. Yes. Maximilian, thanks to you, that same animation was well under 20 minutes in Lua. We will see that animation later. Oh, isn't that amazing? How does this work? I call it technical detail. Don't let that intimidate you. We're going to do another friendly introduction to affine algebra, because sometimes you need to repeat yourself to get the point across. The 3D affine vector is a list of 4 numbers. Most commonly, the last number is 1. In projective algebra, you can change that to do perspective transformations, but we're not dealing with that here. The cool thing about an affine vector is, unlike a linear vector, its origin matters. It really matters. If an affine vector is here, it spans a line through its basis here, not over here. That is very important for navigating subspaces, which is very important for doing things like partitioning and occlusion, which we will get into in small detail as we go along. The important operations are addition, scalar multiplication, the dot product, and the cross product. Addition and scalar multiplication enable navigation. You add scalar multiples of affine vectors in a basis to navigate the subspace spanned by that basis, just like in linear algebra. So if you have 2 vectors pointing like this from a common point of origin, you can traverse the plane through them using just them. It reduces down to Gauss-Jordan, and it is something that I really enjoy, at least. The dot product and cross products are also very cool. The dot product gives us a means of reasoning about angles and projections, and the dot product gives us a means of reasoning about orthogonality. For example, with dot product, I can tell you how far in a specific direction normal to a vector relative to a vector something is. Without the dot product, that would be very difficult. With the dot product, it comes immediately. The cross product lets us generate orthogonal vectors, which point in perpendicular directions to one another. That is useful for developing something called an orthonormal basis, which is useful for a lot of things in algebra. An affine basis for a 3D line segment consists of 2 3D affine vectors. One of them is the origin. One of them is not the other end of the thing, but the direction vector that points to it. So if you had a line segment, the way to turn that into an affine vector would be to subtract the first point from the second point to turn the second point into a vector protruding from the first point to the second point, while keeping the first vector fixed. That turns it into a basis. They can also get turned back into a simplex, but you don't usually do that. An affine basis, and for a triangle consists of 3 affine vectors. One of them is the origin, and 2 of them protrude from the origin. You guys can see how poorly I tessellated down there. That's because I partitioned those triangles so you wouldn't see anything that was on this side of it. Yes, it does not look as good as the original, but it is better than the one that was there this morning. Yes, in this diagram, actually, we use inverse affine transformations to normally, depending on which perspective you take, they're both valid. You can decide to move the camera or move the objects relative to the camera. I like to move objects relative to the camera. So I take the transformation that moves the camera there, and I perform the opposite of it on everything else. It's called an inverse affine transformation, and it's usually how cameras are achieved in graphics. We use matrix multiplications to compose transformations. And the homogeneous coordinate, which is the number 1 at the end of the affine vector, is what lets us do translations. translations are a phenomenal thing to add to linear algebra because it makes it useful for understanding reality. There are lots of nonlinear transformations that are useful. Translation and rotation are pretty fundamental to 3D graphics. And as I've mentioned multiple times, Gauss-Jordan elimination is used to determine the intersection sets of affine subspaces, which are themselves affine subspaces unless they don't exist. But if it does exist, it is an affine subspace. It reduces, it's beautiful. Simplices reducing to problems of simplices. You don't leave that class. It is something I very much like. Simplicial occlusion and partitioning. I promise, I'll keep it basic. Occlusion ordering in the system, the way we do it is we project two simplices, in this case triangles. I'll treat it as triangles. A lot of people find that more intuitive, I would imagine. You project them onto the viewing plane, orthogonally. If they overlap at any point, you sort them by the depth of the inverse orthogonal projection of that overlap point back onto both shapes. You have 2 points, one on each shape. You can order them by the depth using the dot product. And that is, or in this case, I align it along the z-axis, so I don't even need the dot product. And for those of you who are wondering what this is, this diagram took me 16 hours to make in PGF math. 24 frames. And multiple bugs along the way. It took a very long time to make. And this is the same one that took less than 20 minutes by far to produce in Lua, which is why I use Lua now. Simplicial partitioning is achieved through basis navigation and Gauss-Jordan elimination. Gauss-Jordan elimination will take two bases and produce a subspace basis for them if it exists. Otherwise, it'll produce a result that is recognizable to the computer as it does not exist. It might have free variables, or I forget the specifics. And the cool thing is we can navigate that subspace, that new subspace, as a subspace. We get a basis out of this, so we can continue to navigate it the same way we've been navigating everything else. It's basically like steering a ship. It's like driving. Now, this is the big part of the talk. This is the part that I really want to get across to all of you. That's why I put it last. I think that this would be of benefit to the community to hear. There is a gap in parametric tessellation theory that I've noticed, at least. The gap is poor tessellation. Specifically, I am talking about domain restrictions and curvature. I express that in this form of language. Domain restrictions and curvature are the general way to put it, though. Currently, when we tessellate a domain, take it, for instance, for a surface, we will take a Cartesian product of samples along both domain dimensions. And then we will triangulate the resulting grid. By Cartesian product, I mean we take two, usually it's an arithmetic sequence, sometimes it's not, and then we turn them into a giant grid of points based on those two sequences, and then we triangulate those points. This has problems with non-trivial illustrations. I would like to draw illustrations that I cannot draw because of this current technology. I don't have any of those illustrations here today because I only wanted to show good diagrams. But if you're interested, talk to me later. I have a Stack Exchange post that has much worse diagrams that show the issue. When we tessellate a surface domain, it neglects non-trivial, it neglects features relating to domain restrictions and curvature most of the time. And I express that in terms of calculus terminology. So I'm not going to propose a solution here. I'm not here to predict the future. I'm here to inspire you guys to try and fix this problem yourselves. More creative minds focusing on the same thing. Let's overcome this. So I thought of some things that would likely be involved in a solution. Not necessarily, but this is where my mind went. Instead of a generic grid, we would sample the domain, for instance, for a surface, in this case for a surface, based on its parametric properties, for instance, using cast-like capabilities. That would let us identify very specific regions in its domain where it is doing important things, like inflection points or inflection regions if it's a surface. It could capture asymptotes or domain restrictions, and the idea behind that, the idea behind strategically sampling each of these phenomena is that when we go back later, remember the picture of the green, looks like Patrick Starr's pants, someone said? When I removed those triangles on top so they wouldn't go all the way through the ceiling, I did that using something called filtering, using a Boolean filter. If we were to tessellate the domain of a parametric object according to its features and not just a random arithmetic Cartesian product of arithmetic sequences, we could go in and, based on those features, remove simplices that are too close to them or are beyond the boundary. That would be incredibly useful. That would allow us to avoid the asymptote problem, not the software asymptote, the problem with singularities, and the problem of domain restrictions, because not all domain restrictions are asymptotes. But it would let us do that. So the way I was thinking it might happen, I'm not going to say this is how it's going to happen. This is just where my mind went. The sample points in my theory would track the domain boundaries. For instance, they would go around asymptotes, or if the asymptotes spanned a curve, they would traverse around that curve and also along the asymptote. They would also traverse around domain restrictions. And they would not just be adaptive, but they would be deliberately chosen based on the parametric formula. I don't want to reduce this down to just a problem of probability. I want to actually perform rigorous understanding of parametric surfaces using a computer so I can tessellate them better. And it would capture regions of high curvature with more samples, and in order to avoid wasting simplices, which lags our computer by a lot, we would not tessellate so much in areas where it is flat. Currently, when we have a diagram that is, if let's say this floor was a plane, okay, I should probably be on camera, but if we have a parametric surface that is really complicated in one area and not complicated in other areas, why are we wasting triangles in areas that we don't need to waste them in? That slows our computer down. We should not do that.
I think it's lagging.
Yeah.
Okay. How am I doing for time?
I think you're running low.
I think you made the CPU overheat.
Well, I'll talk about this diagram then. This diagram is something very special because we did something here to avoid a tessellation problem. This is a stereographic projection. Ooh. Okay. Thank you.
I was listening.
I'll describe it with the last one because they use the same feature.
This computer appears to have, yes.
So okay, I can't see it anywhere, that's all that matters.
Hopefully this works.
You just wave your hand to the person with permission to crack the computer.
Be accessible, just explain now and
That's right.
There you go.
What's the alt text for this guy?
This was included as an, I don't know if you can add alt text to animations. I'm not familiar with that.
Okay, while we are doing this, could you explain the colophon, how you created animations and how you...
Absolutely, I would be happy to, after we describe the last slide. So, this slide gets into a bit of a more esoteric issue in sampling theory. I debated whether or not I should add it, but the animation was cool, so I did. Intersecting curved surfaces almost always miss the exact regions of intersection. When we essentially tessellate, say, for instance, two spheres, and we intersect them, the result is not actually their intersection, but an approximation of it based on the tessellation. I was actually talking to Charles about this morning, and apparently this is a well-known problem in computer graphics. What I would imagine would be the goal here would be to identify, in order to prevent the need to partition later on, points in the domain where they would map to intersection points. Then we wouldn't need to partition those intersection points because there would already be a partition there. And this diagram is really special because it is a stereographic projection, but as you can see, none of the space is distorted. Normally when you deal with Mobius transformations, some places on the map get really big, and some places get really small. It preserves conformality, but it does not preserve distance. The cool thing about this parameterization is it is a parameterization of the stereographic projection that preserves distances. So circles map to circles under Mobius geometry, and because of that, you can parameterize them in terms of sine and cosine. And there's a theoretical way to prove it. I'm not going to do that here. I do not have a thank you slide. I said my thank yous at the beginning. But as Boris would like to know, and I'd imagine other people maybe who like animations or maybe want to produce their own, how do I do this? The way that I do this is there are multiple ways, but the way I prefer to do it is I use a TeX picture in the standalone document with the TeX document class option. And I usually add a small border around it or no border depending on the illustration. So I would have document class, TeX border equals 1 centimeter, standalone, and then I would use a for each loop on TeX pictures. Because using the TeX class option, each TeX picture will be a unique frame. Now, that will still lead to problems with moving pictures because the frames will be different sizes. You need to use as bounding box. It is very fundamental to that flow. And then once you have the sequence of 24 pages of PDF, in this case, I did something that I don't normally do. I just include animate graphic. I used the package animate to use the command animate graphics to include the PDF. And that is animating the PDF. Normally what I do, though, is I produce GIFs, or GIFs, or however you like to pronounce it. I wouldn't judge anyone for how they pronounce that word, because I don't know how to pronounce it. When I do that, I take the PDF and I use various software, be it ImageMagick, a Python script, or a website, to turn it into a GIF. Thank you.
All right.
Well, I want to keep the duck up.
I know we're running late.
Sorry about that.
And Boris has already had his question answered. If there are no other questions, we can go to the break.
Sorry for taking so long.
Thank you.
What?
We did.
Oh.
That was our side.
Oh, that was yours? Okay.
Yeah, we